Hello everyone, this video covers sections 3.1 through 3.4 from the textbook. From now on, in the class, everything is going to be about random variables. So what is a random variable? So a random variable is a real value function for which the domain is the sample space. So everything, again, like I told you before, will be related to the sample space. So for notational purposes, we're going to use a capital Y to denote the random variable, and then lowercase y, this will be the possible values for the random variable. Okay. Now in chapter 3, we specifically going to talk about discrete random variables. So now we're going to focus just on this kind of variables. So what is a discrete random variable? Well, we talked about discrete variables before, but let's just refresh your memory. So a random variable y, so now we know this is a random variable, is said to be discrete if it can assume only a finite or countably infinite number of distinct values. All right, let's look to a few examples. The first one will be the following. If a family has 3 kids, so we talked about this example before, but now we're specifically focusing on the number of boys. So if a family has 3 kids, the number of boys, the possible values, would be 0, which means they have 3 girls, or 1 boy, or 2 boys, or 3 boys. So these are the possible values for the random variable. Now, if you roll a single die that is balanced, well, the possible values will be 1, 2, 3, 4, 5, and 6. These two examples have a finite number of possibilities. The next one will be countably infinite. Okay, and this is the reason why. If the random variable is the number of trials until you get the first success, well, you can try something and you could be successful the first time, so therefore the value was only 1. Or you failed the first time and were successful the second time. Or failed the first time, failed the second time, and were successful the third time, and so forth. So this will keep going forever, so that's why it's countably infinite. Now, every random variable must have a corresponding probability distribution. In fact, you cannot have a random variable without a probability distribution. And if you have a probability distribution, it has to belong to a random variable. Okay, so let's look to the formal definition. So the probability that y, which remember this is a random variable, takes on the value y, this will be the notation, is defined as the sum of the probabilities of all sample points in S that are assigned to the value of y. And we will sometimes just denote this by this. So this is the fast way to write it, but this means this. Just keep this in mind. Most of the time we will use this. This implies this. All right. So now the probability distribution for a discrete random variable can be represented by a formula, a table, a graph, or a graph that provides the probabilities for all values of y. Now, if we refer back to the example where, remember the family has 3 kids, so we did this in chapter 2, but now here we are focusing on the number of boys. Okay? So then we already say that the possible values for y are 0, 1, 2, and 3. And the associated probabilities, well, we did this before, where you can have a boy or a girl, and then boy, girl, and so forth. Okay? So you should check this. The associated probabilities for this was 1A, then this is 3/8, 3/8, and then finally 1/8. And notice that everything is equals to 1. We'll talk about this in a little bit. Now this probabilities is called the probability distribution. Not very original name, but that's what it is. And every random variable needs to have one. Again, all these values came from this. So we did this in chapter 2. Just check your notes and you see how we got 1/8, 3/8, 3/8, and 1/8. Okay? All right, so let's look to the following theorem, which emphasizes what I just told you in the last example. So for any discrete probability distribution, the following must be true. All the probabilities obviously have to be between 0 and 1. And when you sum all of them, it has to give you 1. Okay, so it should be obvious. So for example, if the random variable is the number of dots observed when a die is rolled, well, the possible values for y are 1, 2, 3, 4, 5, and 6. And the probability of getting 1, remember, is 1/6, 1/6 for each of them. All of these are between 0 and 1, and when you add everything, this is 6/6, which is equals to 1. So therefore, this is the random variable, these are the possible values, and this is the probability distribution. Notice that in this case, the possible values for y are obvious, and the probability are obvious too. That will be the case also in the next example, but sometimes these values are not that obvious, and the probabilities are also not that obvious, and we'll get to that in the next couple of examples. Now here, it says the outcomes if you buy a raffle ticket. Well, you only have two options. You either win or you lose. So what are the possible values? Well, if you win, you will win $498 because you had to pay $2 for the ticket. And if you lose, well, you will lose $2. So these are the possible values for y. And what are the probabilities? Well, since there is 500 tickets, the probability you're going to win is 1/500. The probability you're going to lose is 499/500. And again, notice that when you add all the probabilities, it has to always equals to 1. Otherwise, you don't have a random variable. Okay, let's look to another example. Let's say you have the following game in a casino where the possible values are given like this. The possible values for y will be -3, which means you will lose $3, 0, which means you will break even, 1, which means you will make $1, and 4, which means you will win $4. And let's say that the probability will be that you lose $3 is 45%, that you break even is 25%, that you win $1 is 15%, and then you win $4 is 15%. Again, notice that the whole thing is equals to 1. Now, in this particular case, this is given to you, and this is given. Otherwise, there had to be a formula to figure out these values. Notice that here they should be obvious, and they should also be obvious. Okay, let's do one last example from section 3.2. So the example says the following. You have 5 balls number 1 to 5, and they are placed in an urn. So 2 balls are randomly selected from the 5, and their numbers are noted. So find the probability distribution for the following. Part A, the largest of the 2 number sample, and part B, the sum of the 2 sample numbers. Okay. First, we need to figure out the sample space. So remember, we are selecting 2 from 5. So this will be 5 factorial over 2 factorial times 3 factorial. And you should check that this is equals to 10. So there are 10 sample points, where the sample points are the following. It could be 1 and 2. It could be 1 and 3. It could be 1 and 4. could be 1 and 5. Or it could be 2 and 3, 2 and 4, 2, 5. It could be 3, 4, 3, 5, or 4 and 5. So this is the sample space, which you can see has 10 points, 7, 9, 10. Now the possible value for y, if you are focusing on the largest of the two sample numbers, well, the possible values for y will be 2, 3, 4, and 5. Okay. And then the probability that the biggest one is 2, well, it's only this one, which will be 0.1. Now the probability that the biggest one is 3, well, it will be this and that, which is 0.2. The probability that the biggest one is 4 will be this one, and this one. That's 3, so that's 0.3. And the probability that the biggest one is 5 is 4, which are this. It's right here. This is 0.4. And again, notice this is equal to 1.0. Right, so now we focus on the sum. Well, the smallest sum is going to be 3. And it can go from 3 to 4, 5, 6, 7, 8, 9. The biggest one is 9. You have 5 and 4. And the probability for each of them, well, how many gives you a sum of 3 is only this one, so that will be 0.1. The next one will be also 0.1, because to get a 4, you only have one that will give you a sum of 4. But to have a sum of 5, this is 5 and this is 5, so that's 2, so this will be 0.2. To get a sum of 6, it will be this one and this one. To get a sum of 7, it will be this and this, which is 0.2. To get a sum of 8 is 0.1, and to get a sum of 9 is 0.1. And again, the whole thing has to add to 1. Alright, so notice, and this is going to be very useful later. If I say P5, and this has to do with the notation, in this particular case, this is equals to 0.2. But remember, this is the same thing as the probability that the random variable is equals to 5. Now, if I ask you what the probability that the random variable has a value more than 5, so then more than 5 will be 6, 7, 8, and 9. And then you will have to just simply add these values 6, 7, 8, and 9, which in this case is 0.6. And from here you can also do a bunch of different questions. I could ask you what's the probability that y is greater than 5 given that y is less than 7. So then in this case this will be the probability that y is greater than 5 and y is less than 7 divided by the probability that y is less than 7, and then just look to the values here, plug it in, and that's it. Okay, now let's go to section 3.3, which is the expected value of a random variable or the expected value of a function of a random variable. Now, every random variable has a expected value, and for a discrete random variable, the expected value is defined as this. Expected value of the random variable, which technically you can also say this is the mean, and this is usually going to be denoted by mu. Okay, so expected value and mu for a random variable are the same thing, and is defined to be the sum over all the values of y of the multiplication of y times the probability. So you multiply y times the probability that the value of the random variable is equals to y, and just add all of them. So this is a straightforward calculation. Now, once you find the mean or expected value, you can use that to find the variance. So the variance of a random variable is defined to be the expected value of this. Or in other words, the variance is equal to the expected value of y minus the mean square. And the standard deviation is going to be the square root of the variance, or the positive square root of the variance. Right, so let's look at an example where you roll a die, okay? And these are the possible values. These are the probabilities. We talked about this already. You should check always that this equals to 1, which it is. And then the definition for expected value is telling you to multiply y times the probability, which will be to multiply this times this. So if we do that, this will be obviously 1, 6, it will be 2, 6, 3, 6, 4, 6, 5, 6, and so forth. And once you add everything, this is 21 over 6, or 3.5, and this is the expected value of y, which is also the mean. Alright, since we have the mean, now we can use that to find the variance, and then the standard deviation. There is a square missing there. Alright, so in this case, the first value for y is 1, so it will be 1 minus 3.5 squared, and then times 1, 6. The next one will be 2 minus 3.5 squared times 1, 6. And so 4, the last one will be 6 minus 3.5 squared times 1, 6. And you should check that this is around 2.92. So therefore, for this random variable, the mean is 3.5 and the variance is 2.92, which means that the square root of that will be the standard deviation, and this is around 1.7. Now, if you remember the other example we did with the casino game, for that one we have the following. To remember, for the casino, the possible values for y were minus 3, and then 0, 1, and 4. And the probabilities that were given were 0.45, 0.25, 0.15, 0.15. Remember that this has to add to 1. Then to find the expected value, you need the next column where you multiply the values for y with the corresponding probability. So this is minus 1.35, this is 0, this is 0.15, this is 0.60, and when you add everything, you get negative 0.60. So this is the expected value of the variable y, which is just mu. Now the fact that this is negative, this is the key for casinos to make money. A negative expected value means on average, if you play this game, you should expect to lose 60 cents every time you play. That's pretty much what it means. And all games in Las Vegas or in any casino, they have a negative expected value for you, which means it's a positive expected value for them. Now, the expected value is not limited to just to find the expected value of the random variable y. You can also find the expected value of a function of the random variable y, and that's what the next term tells us. And this term is going to be very important for what we do later in the class. So the term says the following. So let y be a discrete random variable that has a probability function py. Then the following is true. The expected value of a constant is just going to be equals to the constant. This should be obvious. Let's say that if you say that the function of the random variable is just a constant, then by definition the expected value of the constant is going to be equals to the sum for all possible values of y, okay, of the constant times p of y. Since this is a constant, you can just put it outside. So this will be c times the sum of all the probabilities But remember, the sum of all the probabilities is always equals to 1. So this will just equals to the constant. Part B will be a continuation of that, which will say the following: the expected value of a constant times a function of the random variable should equals to just the constant times the expected value of the function of the random variable. And part C says that if you have more than one function, so let's say you have g1 y plus g2 of y, all of them are the same random variable, then that the expected value of the sum is just going to be the sum of the expected values. Good. Right, and again, we're going to use this theorem many times during the class. Now, in particular, notice the following. Remember that the variance of the random variable was defined to be the expected value of y minus mu square. Therefore, if you expand this, this is what I mean by expand, just algebra. This is the same thing as y squared minus 2 mu y plus mu squared, right? So therefore, this will be the expected value of y squared minus 2 mu, since it's a constant, the expected value of y plus the expected value of mu squared. So this is the case by using part C and part B. So then this is the same thing as the expected value of y squared minus 2 mu. But remember that the expected value of y is also mu. This will be mu. And since this is a constant, or the expected value of a constant is just the constant itself, so this reduces to the expected value of y squared minus mu squared. So this is another formula for the variance, and this is actually computationally probably easier to use than the other one. So this will be one of the most common formulas for the variance. So we will use probably this more than this version, even though they are the same. Alright, so in the next page we will use now this formula to find the variance. Right, so remember that in the last page we just got the variance. Remember, this is the variance of y is the expected value of y squared minus mu squared, or you can say that this is the expected value of y squared minus the expected value of y, the whole thing squared. Okay. So we fill out this table already. Remember, this was 1 6 2 6 3 6 4 6 5 6 and then 6 6, and this one was 3.5, which meant the mean was 3.5. Remember, this is also the expected value for the random variable. Now this one telling you to square y and then multiply times the probability. So if we do that one, this will be 1 6. Now it will be 4 6 9 6 16 6 25 6 and then 36 6. And once you add everything, this is 91 over 6 or 15.17. Okay, so you should check that. So we use the new formula, then the variance will be the expected value of y squared, which is 15.17, minus the expected value of y, which is 3.5 squared. And this should give you exactly the same thing we got before, which was 2.92. And again, if you want the standard deviation, it will be the square root of that. So this is the standard deviation, and this is around 1.7. All right, so let's use the last term a couple more times. So these are very interesting problems. So let's say you have the following random variable where x is defined to be the random variable y plus 1. And let's say I want to find the expected value of y. So the expected value of x. So the expected value of x is equals to the expected value of y plus the expected value of 1 from the last term. And assuming here that the expected value for y is equals to mu, then this is obviously just mu plus 1, because remember, if this is a constant, expected value of a constant is 1. That was self-explanatory. So then the variance of x is going to be the expected value of x squared minus the expected value of x squared if we use the new definition, which is this one, the one we just got in the last page. Well, therefore this will be equals to this part will be the expected value. X squared is going to be y squared plus 2y plus 1, and then this one, you already know that the expected value of x was equals to mu plus 1, so this will equals to mu plus 1 squared. Right, so this part is this, and this part gives you this. So if you expand this, it will be the expected value of y squared plus 2, plus 2, the expected value of y plus the expected value of 1 minus mu squared plus 2 mu plus 1. Right, so notice this will cancel this, and this obviously will cancel that, so you'll end up with the expected value of y squared minus mu squared, which is technically just the variance of y. So therefore this result is very important, which means the mean will be different if you add 1 to the variable, but notice that the variance of x and y are exactly the same. So the variance of x and the variance of y are the same, even though y is the variable x plus a constant. Right, so now let me do a general result for variances, which are going to also be used a lot. So let's say now we have a new variable, let's say, I don't know, t is equals to ay plus some constant. So obviously from here, the expected value of t, which is going to be a times the expected value of y plus the expected value of a constant, which I already said was a constant, so it will be a mu plus c. Okay? So that's not that hard to do and not that interesting. The variance will be more interesting. So what is the variance of t? So the variance of t is going to be the expected value of t squared minus the expected value of t squared, which will equals to the expected value of a squared y squared plus 2ay plus c squared minus a mu plus c squared, where this is a squared mu squared plus 2a mu c plus c squared. So this is very similar to what we did before. So this will be a squared, the expected value of y squared, plus 2a mu plus c squared, and then it will be a squared mu squared minus 2a mu c minus c squared. And there is a c missing here. So you can see the c squared will cancel this one. The 2a mu c will cancel the 2ac mu. So what you have left is you can factor the a squared. It will be the expected value of y squared minus mu squared. So this is a squared, the variance of y. Okay. So again, this is going to be a very useful result. The variance of this is just the square of this times the variance of that, and the constant doesn't matter, which makes sense. Variance means how things are changing, so a constant doesn't change, so this should be 0. That's why there's no c here. All right, so this is the end of 3.3, and up to this point we have talked about discrete random variables in general. For the next sections, we're only going to go to 3.4 right now in this video, but from 3.4 and on, we're going to talk about specific random variables. And the first one we're going to talk about is the binomial distribution, or the binomial random variable. So a binomial probability distribution has the following properties. First, you're going to have a fixed number of trials, which is going to be n. Okay, so a fixed number of trials, n, and each trial has only 2 outcomes, and the 2 outcomes is that you are either successful or you fail. Now the probability of success for a single trial is going to be called p, so therefore the failure is going to be 1 minus p, which is usually denoted by q, and each trial is independent, and the random variable of interest is going to be y, so we're going to focus on the number of successes in trials. So technically, if you try something 10 times, how many times are you going to be successful out of 10 times? Now, if you try something 10 times, the worst thing that can happen is that you fail every single time, like the Clippers or Mexico in every World Cup. And the best thing that could happen is that you are successful 10 times. Okay? So this is a smaller number of successes you can have, and n is the maximum number of successes you can have. To find the probability of the number of successes, all you have to do is use the formula, which technically it makes a lot of sense. So P is the probability of success. So the formula is technically counting all the different ways in which you can be successful, but you also have to take into account all the way in which you can fail. For example, let's say if this was 4, and let's say that n is 10 again, so then it will be 10 choose 4, and then whatever probability we have to the 4 power, then 1 minus p to the 6 power, meaning that if you are successful 4 times, then that means you fail 6 times, and this will count all the different ways in which you could be successful 4 out of 10 times. That's it. So that's what the formula technically is doing. So let's do a concrete example. The problem says the following: approximately 15% of Californians are vegetarian. So therefore here, being vegetarian will be considered the success. So therefore the probability of success will be 0.15. So therefore the failure, which is 1 minus p, will be 0.85. Okay. So if you randomly select 10 Californians, so let's say that n is 10, what's the probability that exactly 3 of them are vegetarian? Well, here the value for y is equals to 3. So we're trying to find p of 3, which will be 10 choose 3, and then 0.15 to the third power, and then 0.85 to the 7th power. Right, so then you just use a calculator and compute these values. If you have a TI-83, it can compute the whole thing for you at once, and the answer is 0.1298. So you have a TI-83, you just have to go to second variables and just find the binomial PDF function, and it will give you the answer automatically. It's not needed to have one of those because you can just compute this by hand, and actually on the exam you may just have to leave the answer like this. All right, so part B, using the same information, says what's the probability that at least one is vegetarian? So now at least one means y is greater or equals to 1. Now in this case you don't want to do this directly because more than one means, at least one means 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you have to do this 10 times. So instead you should do the complement, which will be 0 or none. So then it will be 1 minus, should be 10, choose 0, times 0.15 to the 0 power, and then 0.85 to the 10 power. Now in this particular case, remember that anything to 0 is 1, anything to the power is 1. So for this particular case, this is just 1 minus 0.85 to the 10 power. And then whatever that is. Now part C says, what's the probability that at most are vegetarian? So therefore y is less than or equals to 2. So then it will be y equals to 0 plus y equals to 1 plus y equals to 2. And then you just do each of them separately. 0 will be 10, choose 0. We did this one already. Then this will be 0.15 to the 0 power, 0.85 to the 10 power. Then the next one will be 10, choose 1, 0.15 to the first power, and then 0.85 to the 9 power. Then the last one, it will be 10, choose 2, 0.15 to the second power, and then 0.85 to the 8 power. Okay, so again, in case you haven't noticed, this plus that has to add to n, and this plus that has to add to 1 all the time. Now, since the binomial distribution is also a random variable, it also has a mean, and it also has a variance and a standard deviation. But for the binomial, it's pretty easy to compute, like you will see in the next page. So if y is a binomial, and p, this is usually how we're going to denote it now. We're going to say y is binomial distribution and p. So it is what we have. Then we're trying to figure out the expected value. So remember, by definition, the expected value is equals to the sum of all the values of y, which is from 0 to n, of y times p of y. Now for the binomial, specifically, remember that p of y is equals to n choose y, p to the y, 1 minus p to the n minus y. Now notice that since the first value of y is 0, anything times 0 is equals to 0. So therefore this sum actually doesn't start until 1. So it's y equals to 1 to n of this. Okay, so that's going to be very important. Also note, so it's going to be very useful for the proof we're trying to do here. If we do y times p of y, what we already said is y equals to y times, now this will be n factorial, This is y factorial, n minus y factorial, and then this is p to the y. Okay, so this and this is the same thing so far. Right, so notice that y factorial is the same thing as y times y minus 1 factorial. So by doing that, this y will cancel this y here. And also notice that n, you can rewrite it as n factorial as n times n minus 1 factorial. Okay, so far this is what you have. You have n times n minus 1 factorial. And then on the bottom, this is just y minus 1 factorial times n minus 1 factorial, and then times p to the y minus p to the n minus y. Next, you can multiply this by p and divide by p, which means you're multiplying by 1. And that will give you the following. You can take out the mp, which will be this part. And then this will be n minus 1 factorial. Okay, n minus 1 factorial. This will be y minus 1 factorial, n minus 1 factorial, and then it will be p to the y minus 1 now, and then 1 minus p to the n minus y. Right, so this is what we have so far. Then from here, this will equals to mp, you can take outside. This will be the sum from y equals to 1 to n of n minus 1 factorial, y minus 1 factorial, n minus y factorial, times p to the y minus 1 and y minus p to the n minus y. Alright, so now let z equals to y minus 1. So if that's the case, then we're gonna still have mp, and then this will be the sum from z equals to 0 to n minus 1. And then here you have n minus 1 factorial. This will be z factorial. It will be n minus z minus 1 factorial. Then p to the z, and 1 minus p to the n minus 1 minus z, which is equals to np times the sum from z is equals to 0, n minus 1. And now this is the same thing as n minus 1 z, p to the z, and then 1 minus p to the n minus 1 minus z. Now by the definition of the binomial random variable, this is equals to 1. So therefore this is equals to np. So therefore for the binomial, the expected value of y is equals to np, which makes finding expected value for binomial random variables very, very easy. For example, in the last example we did, remember p was equals to 0.15 and 1 was equals to 10. So therefore the expected value there will be 10 times 0.15, which is 1.5. Now to find the variance is also very, very easy. The variance for y, and you should check this, is equals to mp times 1 minus p, or mp q would be the variance of y, which, remember, this is the symbol for variance, sigma square. So you want the standard deviation, you take the square root. Now to get this formula, you can do the similar process to what I did here. It's a little more messy, but remember, to get the variance of any random variable is equal to the expected value of y squared minus the expected value of y squared. So this is all the work we did here is to get this. So you have time, just give it a try, and it's more time consuming than this one, but it's not impossible to do. And you will end up with this. All right, so therefore you want to find the variance here in this particular example. The variance will be just 10 times 0.85 times 0.15 times 0.85. That's it. Okay? So finding the variance and expected value for a binomial random variable is as simple as this. Now you don't have to derive the formula every time. If I ask you to find the expected value of a binomial random variable, all you have to do is multiply n times p, and for the variance n times p times y minus p, or n times p times q. Okay, and that's it.